A catalyst can be used to speed up a chemical reaction. Its role really in a process can be to lower the energy demand of that process. So essentially the catalyst is something that's not consumed under a process. It continually turns over reagents and converts them into a high value product.
Catalysts are really important for the chemical industry. So something like 90% of all the products that we have around us are made at some point with a catalyst in their production. And so catalysts contribute about £18 billion to the economy.
Working out the structure of a catalyst is very, very difficult. We have to measure the behaviour of that catalyst species under working reaction conditions, we say. So the method that we've developed in York to study catalytic processes is one where we can go down to a very, very fast timescale. So by that, normally we think of timescale as seconds, minutes and hours, days and so on. Down by about 10 to 12 orders of magnitude to picosecond timescale.
Picoseconds are really fast, so they're about 1/1,000,000th of a second. If a catalyst is a good catalyst, by definition it has to work quickly. Any process that it does, any bonds that it's forming, any bonds that it's breaking, they have to take place on a very fast timescale.
This is where all the action happens. So we have a range of ultra-fast lasers and spectrometers that can look at changes that are happening in chemical reactions on timescales all the way from a millionths of a second right out to seconds timescales. We use the light in the laser system to trigger reactions when we want to, and then to probe them, to watch them, to monitor how they progress. So in these catalytic experiments, we've actually made molecules that react to light, so you can trigger that reaction off when you want to with the lasers. I have a little sample here and a flash gun, and I take the flash gun and I point it at the chemical and flash the gun. See, it changes color. The molecule has changed its structure, and that caused the sample to change color. So this is basically what we do here with lasers. We trigger a reaction with one pulse of light, and then we watch what happens with the reaction with another pulse of light. The catalysis work, we're using infrared light, and that's sensitive to the molecular bonds that are changing within these reactions.
So you're looking at the front line here. So using the spectroscopic technique, we're able to directly look at the reaction steps when hydrogen is bonded to a carbon atom, is replaced with a new atom using transition metal catalysts.
We're really lucky. We've got a large collaboration with the guys down at the Central Laser Facility in Oxfordshire. We normally take one of the more stable intermediates of our reaction from our stuff here at York, and using the laser there, we're able to start off the reaction and follow the various steps in the mechanism as it proceeds.
By making sure that you've identified the correct catalyst for the reaction, it will decrease the cost of a particular substance, because if we want to make our pharmaceuticals, if we want to make our agrochemicals in a much more efficient manner, that will therefore drive the price of them down, and so to the consumer it will mean that they have to pay less as well. And that's in addition to making sure that the environmental aspects of catalysis and the chemical industry is improved as well.
We've got a very talented team here in York, but we also collaborate with scientists at the Central Laser Facility. But it is the enthusiasm, their dedication and determination at times of those people that really make this project come alive, I would say, but the success it's been as well.